Hello, ENB 460 students. My name is Jerome Ramirez. I'm a chemical engineer and currently a PhD student doing lots of Aspen modeling. I'm here to help Dr. Rainey and Dr. Ford in the Aspen lectures. So, as you might know by now, Aspen can model a wide range of processes, but what's particularly important to you at this point is solids processing, which is what this week's lecture is about. Okay, so we just open Aspen Plus. Right, and while waiting, we'll look at the exercise. As soon as the window closes. So, this lecture involves milling of solid biomass and drying, but for this video, we'll just deal with milling. And then for the next video, we'll go into drying. Right. So in this first part, we'll model the milling of 10 tons an hour of biomass, which in this exercise will be eucalyptus pellets to reduce its particle size. So milling is especially important when dealing with solids because, for example, for boilers, we need a top size or the largest diameter so we can reduce clogging or blockages in the fuel handling system. In some other processes like pyrolysis or gasification, particle diameter is specified to reduce heat transfer resistance. For example, in pyrolysis, fast pyrolysis, the process happens quickly. So if you have a large particle, heat transfer and thus the reaction will happen um, slower than if it's a smaller particle. That's why milling or size reduction in these processes involving solids is important. Okay, so in this lab we have several givens which we are going to work through. So we have installed templates in Aspen under solids. We'll look at that in a short while. And then we're going to use non-conventional materials. We're going to use the ideal base method. And then using met solid as the global unit set. And a new stream class called mix NC PSD, which just specifies that we're going to use non-conventional, which is the NC here, and using a particle size distribution, which is the PSD there. Right, so let's get to Aspen. Alright, so if we go to new and go to the solids templates and choose solids with metric units. Right, and click create. So your solids could be in different forms, like a conventional material that's also a solid, like carbon or silicon, or a non-conventional one, which is likely a biomass feedstock, or even um, something like coal. So for this exercise, we'll say that we are entering biomass. and then changing the type from conventional to non-conventional. Right. So when I did that, this blue tick appeared here, which means it populated the table with biomass as a non-conventional component. And then we have to look at which fields have the red circle and address that. So going back to the exercise sheet, we see that the base method we're going to use is ideal, global unit set met solid. So choosing ideal and looking at the specifications, you see global unit set is met solid, which automatically loaded itself when we chose met solid template. So that's convenient. And then going back to the red circles, we see NC props is red. Right, so at this dialog, we see that for our component biomass, a non-conventional component, we need to specify how Aspen estimates the enthalpy and the density. Okay, so for this one, we're choosing H-gen for enthalpy and DCO ALIGT or decol IGT for estimation. So the choice comes from just general col estimation methods for enthalpy and density. So H-gen calculates enthalpy of the non-conventional materials using the sum of the heat of combustion, the heat of formation of combustion products like carbon dioxide, water, carbon monoxide, and also the sensible heat difference from the reference temperature, which is 298.15 Kelvin. Then decol IGT is estimated from the IGT model. So IGT means Institute of Gas Technology. Uh, this one's more complicated to explain, but a tip if you can't, if you run to something that raises questions, you can hover around the dialog. So it says what I just said, cold density model based on IGT correlation. If I want to know more, at this point I can just press F1 on my keyboard and the Aspen Plus help window appears, and then you can just look at the explanation for this window. I can also use search to say I want to know more about decol IGT. I can say decol IGT, press enter, and find out more about what I need to learn here. It gives a very long explanation there. And for those of you wondering what that is, you can learn more about that using help. And Aspen has been very good with providing modelers with this background information conventional properties. So we can move on to simulating the milling process. Okay, so moving on to the simulation tab. First thing we need to do is to create a stream. Creates stream 1, which for convenience I will now name biomass. Just so you know, I know what that stream is, because if I use numbers, like when I'm modeling, I usually use names because when I use numbers, I get confused. Like what number a certain stream I want to access is. So I can give my streams names, and when I finalize my model and have the stream table ready, I just rename everything to numbers because I don't need to manipulate the streams anymore. So anyway, that's just a handy tip for modeling. So we need this biomass stream to be mix NC PSD specified here. Stream class mix NC PSD. And we can change the stream class by right clicking on the stream and going change stream class and just choosing mix NC PSD. Clicking OK. Right, so going back to the input, we can see that the NC solid tab is checked there and specify same. So since we don't have any other components, we can just get rid of that and just work on the NC solid tab. So again, specifying 10 tons an hour. And with just all biomass. So the mass fraction of biomass is 1. Okay, so if this was a conventional material, then it's all done. But for non-conventional materials, we have to specify component attributes. And since we said we're specifying this stream using a particle size distribution, we also have to enter some data in there. Okay, so for the specifications, we can um, enter proxanal, which is proximate analysis, and ultanal, which is ultimate analysis. And then there's another one called sulfanal, which is sulfur analysis. You can usually get this in literature if you're working with a particular kind of biomass or even a mixture of biomasses. For this exercise, we're using eucalyptus, and the values of the proximate analysis and the ultimate analysis has been provided for us. So we have more. It's common in these biomass studies, literature, journal articles, books that they provide this characterization for the biomass used. And when we go on Aspen, it's the same. So for component biomass, the attribute proximate analysis. So remember, it's weight percent in dry basis, except moisture. So remember that proximate analysis is in weight percent in dry basis. So when you see values in literature, you have to make sure that you convert it to dry basis before you enter them on Aspen. So we'll just enter values from what we're given. So that's 52 for moisture, 6.1 for FC, 40.2 for VM, and 1.7 for ash. Yep, and you can see blue tick. That's complete. Now doing ultimate analysis. So ash is 3.5. Carbon is 23.4. Hydrogen is 2.8. Nitrogen 0.1, same for chlorine, same for sulfur, and then oxygen would be 20.1. Right, so that's done. Blue tick mark. And last is sulfate, which in this exercise we just specify organic sulfur as 0.1. Okay, so component attribute is done. We're moving to particle size distribution. So when we look at the data provided for us in this exercise, we see this particle size distribution. So this stream, the biomass stream, is the one coming in to our milling process. So we expect that a larger particle size is present in the biomass stream. Right. So this particle size distribution shows us that the smallest particle size is 25 millimeters and the largest is 50 millimeters. And then this particle size distribution is fairly simple. We're saying that 10% is between 25 and 27.5 millimeters, and 10% is in between 27.5 and 30 millimeters, and so on until it gets to 50. That's the particle size distribution, and we potentially want to reduce that particle size distribution to the one up here, which is 7.5 to 25. But when we enter it as the biomass particle size distribution, we say that there's no particles in those ranges. But when we make the particle size profile, we just need to include these smaller sizes so that they can be included in the analysis after our milling process. Right? So going back to Aspen, we have this already made for us. It's 0 to 20 mu up to 180 to 200. But that doesn't match exactly what we have in our data sheet. So we need to click Edit PSD Mesh to change that. Alright, so we have this. So counting the intervals, it's 17 intervals. So we just put 17 in there. Yep. So there's two ways to do this. Either just type the values directly, 7.5, and then 10, and then the next one is 10, 12.5, and so on. This works particularly if the intervals aren't equally spaced or there's no pattern with the intervals. But if we have something that has equal intervals, we can just choose in the PSD mesh type drop down, we can just choose equidistant. Okay. And then looking at the datasheet, we see that the lower limit is 7.5, the upper limit is 50, and the size is in millimeters, right? So lower limit is 7.5, upper limit is 50, size unit is in millimeters, and the number of intervals is 17. So going back to the datasheet, just to show you where I got that. Counting the intervals, it's 17, 1, 2, 3, 4, 5, and so on to 17. The lower limit is the smallest size, which is 7.5, and the upper limit is the largest size, which is 50. So when that data is complete, we can click Create PSD Mesh, and that populates the table. See, 17, 47.5 to 50. Upper limit is 7.5 to 10. And click Next. So we have the mesh on here now, and we can start to enter the weight fractions. So remember, from 7.5 to 25, weight fraction is 0, and from 25 to 50, it's 0.1. So entering the value 0, the cumulative weight fraction just calculates from your input. And then just entering 0.1, 0.1, 0.1, until you complete the whole table. Another way to speed up the process is that if you have the values in an Excel spreadsheet and all the values are aligned like this, just make sure that the values correspond to the right intervals. If you have that in an Excel spreadsheet, select the column, click copy, and then click paste here, or Control V here, and it will just paste the values. So that's a quicker way to do it. Right, so now that we have entered the particle size distribution, the blue check mark appears beside particle size distribution. So this stream is now alright. Going back to the main flow sheet, to create the milling process, we have to go to Solids tab on the model palette. Click that. And choosing a crusher operation. Right. So there's many types of crushers here, but for this exercise, we'll just choose the simplest one, which is this one, Solids Crusher, General Crusher, and create a crusher right there. Okay. Right. So next step is to connect the stream by right-clicking and choosing Reconnect and Reconnect Destination, because that's our input right there, and then creating a material output or product. Right. So it's up to you to rename it. I'll rename it milled. Okay. So we have that. We have our streams connected to the crusher, and now we specify inputs for the crusher. Right. So selecting the crusher type, which is single roll. And when we selected that, the selection function and breakage function automatically specified US Bureau Mines, which is fine. Just leave it as that. And then we specify maximum particle diameter as 0.25. So we also have to specify how the grindability is calculated. So in this exercise, we select Kick's law for the comminution law and specify the bond work index given to us as 87.28. So same for both streams. Right. So the exercise gives us values for the bond work index and the Hardgrove grindability index. But Aspen calculates the Hardgrove grindability index from the bond work index. So again, if you don't understand any of this or just have questions about it, hover and see what information it gives you, or just press F1. Alright, so having specified that, we see that the grindability tab has the blue check. Alright, so it looks like we might be ready to start the simulation. So one way to check it is to click next here. There's also a next button there. Doesn't matter, you can click either of those. And then if it's complete, the simulation will start. But if there's an error, for example here it says block not complete, B1, all streams are not the same class. So of course when you have just a unit operation, it's like Aspen expects that the stream class is the same. So we specify that as mix NC PSD. We should also specify that. The same, mix NC PSD. And that makes sense because it's just a physical process. So the stream class of the input should be the same as the stream class of the output. Clicking next. All required input is complete. Let's simulate. Okay, so look, from particle diameter is 0.25 meters, but we really wanted 25 millimeters. So conversion is important here. So if we add a 0 there, that should be 25 millimeters. Yeah. So I changed that, and the moment I changed that, all these icons had a yellow diamond, which means I changed an input. And let's see if I'm ready to run the simulation again. Required input complete. Okay. And let's see. Right, yeah. So this is where we want it to be. So just changing the particle diameter from 0.25 meters, which is 25 centimeters. That's too big for our purposes. We needed 25 millimeters, which is 0.025 meters, and now we get a more sensible power, which is 15.6 kilowatts. All right, so with that flow and with that particle size specification, we calculated the power requirement. And this is important when you're specifying a crusher, you need to specify the power requirement, and you also need the the power used in calculating for operating expense. Right. Okay, so we've successfully modeled a crusher that reduces biomass particle diameters from a larger particle distribution to a smaller particle distribution. Yeah. So let's just look at the new particle distribution. So if you can remember, our input particle distribution is from 25 millimeters to 50 millimeters. So going to home and clicking stream summary, so we can see all the streams in one table. Alright, we can see biomass and milled stream side by side. It's easier to compare. It's so much easier to compare two different streams in this view. So if we go to solids and select particle size distribution and click fractions, we can see the particle size distribution. So we see that for biomass, the distribution is from 27.25 to 27.5 and up to 47.5 to 50, it's just 0.1. But for the milled stream, we've had smaller particle sizes. Right? So the smallest particle size now is 7.5 to 10, which is this fraction. Oh, good. Right. And because we have that initially set up, you can play around with the specification. So it would be interesting to see what the effect of the power specification is for the particle size interval, or the largest particle size that we can generate. So if we go B1 input and change the power requirement or power specification, we can see the effect to the maximum particle size. And this is particularly helpful because if we just specify the particle size and come up with a power requirement, sometimes probably a piece of equipment with that power specification is not available, and thus we need to get a crusher off the shelf with a particular power specification. So for example, I just have one with 10 kilowatts. So I select power specification here, and I change that to 10 kilowatts. So with our initial specification of 25 millimeters, we see that we needed 15.6 kilowatts to do that. So if we select a crusher with a lower power specification, what what could possibly be the effect of that to the particle size? We can simulate that by changing power specification to 10 kilowatts and clicking next. and simulate. So possibly because there's less power crushing your biomass, then we'll expect a larger particle size, maximum particle size. Right, so simulation has completed. The blue checks are in. We can look at block B1 results. Yep. So it ran the simulation at 10 kilowatts, 9.999, close enough. And then looking at the stream summary, particle size distribution, we see that the profile is different. If you can remember um, the particle size distribution earlier, it's quite different. Right. So from 15 kilowatts, we see that the bottom ones, the bottom rows, had zero fraction, but now we have 0.015, which is 1.5%. It's still in that large particle range. So reducing the power increases the maximum particle diameter. Right. So what if we increase it? So we now have 10. We can increase it in 5 kilowatt increments. So change 10 to 15, run, change 15 to 20, run, and then see what the maximum particle size interval is. Right? I'll let you do that by yourself, but you should see that as we increase the power, we also reduce the maximum particle size interval. Right? So that's it for this video. We'll discuss the next section, drying, in the next video. But when you do your milling simulation, please save the file because we're also going to use the same file for the next section on drying. Save. And that's it for this video. Thank you for listening.